Sampling distribution summary. We tackle probability problems involve categorical or quantitative variable. With categorical variable, we often compute the proportion. Suppose we have a population with the parameter p. P represents the proportion of the population, and we perform the sampling distribution by taking repeatedly samples of size n, and we compute the proportion p hat 1, p hat 2, p hat 3, and so on. We obtain these p hat, and when we take a look at this distribution of these p hat is called the proportion of the sample, which we call it a statistics, and there are many p hats here. The distribution of this p hat has a center that had the same at the center of the population, and so it is the same as p. P again is the population proportion, where p hat is the sample proportion, and so with the distribution of these samples proportion, the center is p, and the spread is the square root of p times 1 minus p over n. This expression is entirely underneath the square root, as long as the condition n times p is at least 10 and n times 1 minus p is at least 10. And if these two conditions are met, then we obtain a normal bell-shaped curve, approximately, with the mean p and the standard deviation the square root of p times 1 minus p over n. With a quantitative variable, we do the same thing. This time, the mean, because it is quantitative, the mean of the population is mu and the standard deviation is sigma, and we repeatedly obtain samples of size n. We would compute the mean. In this case, it is x1 bar, x2 bar, x3 bar, and so on. The parameters for the quantitative variables is mu or sigma. Mu for the population mean and sigma for the population standard deviation. When we take a look at this of the sample, we compute the mean, but the mean for the sample is now x bar, and the standard deviation for the sample is denoted using the lowercase s. And so 1 is for the population, 1 is for the sample. These are called the parameters, and these are called the statistics. We expect the sample has a mean or the center at the same at the population mean, which is mu, but the standard deviation is smaller than the population standard deviation, and that is sigma divided by the square root of n. The shape is normal if the distribution was already normal. If it's normal, then the sampling distribution is normal. There is no other condition. And so we require that the distribution is normal to start out with. If not normal, then we need the sample size to be at least 30 for the sampling distribution to be approximately normal. And again, if the original distribution is normal, then the sampling distribution is exactly normal. If the distribution started out not normal, then we can turn it into a normal distribution using the sampling distribution as long as the sample size is at least 30. Once we obtain the normal distribution with the parameters mean, mu, and the standard deviations nu, sigma, remember that there is a correction for the standard deviation here. We then draw the bell-shaped curve and start solving the problem using normal distribution. This result, when we perform the sampling distribution with repeated samples, is called the center limit theorem in statistics.